Today we are walking through the paper titled Thinking Without Words: Efficient Latent Reasoning with Abstract Chain of Thought.
Start with the main idea. What problem is this paper trying to solve?
The paper is about making chain of thought reasoning cheaper at inference time. Long written rationales can improve hard reasoning, but every extra reasoning token costs time and compute before the model can answer.
So the goal is not just to shorten the reasoning, but to keep the answer quality?
Exactly. The authors propose abstract chain of thought, or abstract COT. Instead of writing a natural language rationale, the model emits a short sequence of reserved abstract tokens, then uses those tokens to produce the final response. The first visual shows the basic contrast. On the left, verbal chain of thought writes step after step in natural language. On the right, abstract COT uses a compact abstract segment between special delimiters before the answer.
Where do those abstract tokens get their meaning if they were reserved tokens?
That is the central training problem. The paper warms up the abstract vocabulary by using a teacher verbal rationale at first, but it forces the answer to depend on the abstract segment rather than directly reading the verbal rationale.
What makes the warm-up a bottleneck rather than ordinary supervised fine-tuning?
During bottlenecked supervised fine-tuning, the abstract tokens can attend to the prompt in the verbal rationale, but the answer is masked so it can attend only to the prompt in the abstract tokens. The verbal rationale has to be compressed through the abstract segment.
After that, does the model still need the teacher rationale at inference time?
No. The self-distillation stage trains the model to generate abstract tokens from the prompt alone with constrained decoding. Then reinforcement learning samples abstract traces and responses, scores the responses, and updates the model over that constrained action space. Here is the probability view. The response probability is written as a sum over possible abstract traces. In words, the model first chooses an abstract trace for the prompt, then produces the answer conditioned on that trace.
Why not optimize that sum directly?
Because the space of discrete abstract traces is huge. The paper treats the exact marginalization as intractable, so it bootstraps the traces, first with verbal guidance, then with self-distillation, and finally with reinforcement learning. The information bottleneck is also expressed formally. The answer's dependence on the verbal rationale is bounded by the information carried through the hidden states at the abstract token positions.
So the abstract length controls how much reasoning information can pass through.
Right. The hidden states scale with the abstract sequence length. A smaller budget makes the channel tighter, while a larger budget can carry more information for difficult reasoning.
What did they compare it against in the experiments?
They compare abstract COT against the initial baseline and against verbal chain of thought trained with supervised fine-tuning plus reinforcement learning. The benchmarks cover math reasoning with MATH 500, instruction following with Alpaca Evil, and multi-hop question answering with Hotbot QA. The main result plot puts quality on the vertical axis and generated tokens on a log scale horizontal axis. The desirable direction is up and left better score with fewer generated tokens.
What should I compare first in that plot?
Compare abstract COT with verbal chain of thought after supervised fine-tuning and reinforcement learning. On the plotted tasks, the abstract COT points it much farther left, meaning many fewer generated tokens, while their scores stay close to or above the verbal counterpart. The headline number is that abstract COT reaches up to 11.6 times fewer reasoning tokens while maintaining comparable performance across the tested math, instruction following, and multi-hop reasoning settings.
Does the method still work when the model size changes?
The appendix checks a larger Q and 3-Chitobi model. The abstract COT outperforms verbal chain of thought on Alpaca Evil and Hotbot QA while using 2.7 in for 0.4 times fewer tokens. And it nearly matches MATH 500 with 11.0 times fewer tokens.
The paper also says the abstract tokens become language-like. What evidence supports that?
During reinforcement learning, token use stops being uniform. One token becomes much more frequent, and the final frequency distribution follows a power law shape similar to zip-like patterns in natural language.
Should we interpret that as proof that the tokens are human-readable concepts?
No. The claim is more careful. The distribution suggests reusable structure has emerged in the learned codebook. The tokens help the model root reasoning internally, but the paper does not claim that each abstract token maps cleanly to a human word.
What are the main limitations or open directions?
The discussion points to budget limits. Very small abstract budgets may be too tight for long horizon reasoning, so difficulty-aware sequence lengths could be useful. The authors also suggest that hierarchical codebooks might support reusable reasoning supertimes.
Give me the final takeaway in one pass.
The paper shows that a model can be post-trained to reason through a short discrete abstract trace instead of a long written rationale, with bottlenecked warm-up, self-distillation, And constrained reinforcement learning. Abstract Gochi cuts reasoning tokens sharply while staying competitive on several reasoning benchmarks.
So the contribution is an efficient reasoning interface inside the model, not just a shorter transcript.
Exactly.